In this video, we're going to be talking about simple probability. So an experiment is an event that has varying results, and these results are called the outcomes. What we're going to be looking at today is figuring out how many possible outcomes there are in a given situation. So for example, how many possible outcomes are there when flipping a coin and when rolling a die? There's two ways we can visualize potential outcomes, and that's going to be by creating a sample space or a tree diagram. So when we flip a coin, let's think about this for a second, we could either get heads or tails. When we roll a die, we could get 1, 2, 3, 4, 5, or 6. So we're going to represent this in both a sample space and a tree diagram. So a sample space is like basically a list of all of the combinations. So I'm going to put it in set notation. So we could get heads with a 1, right? We're kind of listing all the combinations. We could get heads with a 2. Heads with 3, heads with 4, heads with 5, heads with 6, and now we could also have gotten tails with 1, tails with 2, tails with 3, tails with 4, tails with 5, and tails with 6. Notice here we have 12 possible outcomes. We could also create a tree diagram. So a tree diagram looks like a tree, has branches, that's why it's called that. So we start off with the first event, which is in this case flipping a coin, and that means we get heads or tails. And then we're going to draw branches off of it. So with heads, we are going to have 6 branches because there are 6 possibilities. So we could get 1, 2, 3, 4, 5, 6. And then we're going to do the same thing with tails. So 1, 2, 3, 4, 5, 6. And you can see, again, we have 12 possible outcomes. There is one other way to calculate how many possible outcomes that we could have from an event, and that's using something called the fundamental counting principle. So we can use the fundamental counting principle to determine the total number of possible outcomes. If one event has m possible outcomes and a second event has n possible outcomes, the total number of possible outcomes when both events occur can be found by multiplying m times n. If you think about this in this example, we had 2 possibilities, 2 outcomes that are possible for the coin, 6 possible outcomes for the die, and 2 times 6 gives us 12, and that matches our 12 outcomes from our sample space and our tree diagram. If we look at another example of this, it says how many possible outcomes are there when randomly selecting a letter from the alphabet and when rolling a die? Well, there are 26 options we could pick from the alphabet and 6 options we could get from rolling a die. So if I multiply those, I would have 156 possible outcomes. And to kind of put this all together, probability is the likelihood that a particular event occurs. So the probability of a given event, we use these parentheses to notate what we're looking for, is the number of favorable outcomes divided by the number of possible outcomes. So it's kind of like we just figured out the denominator of that fraction, how many possible outcomes there are, and we'll talk about how many favorable ones there are when we look at some sample questions. All right, so let's take a look. All right, number 1, create a sample space that represents all possible outcomes from flipping a coin and drawing a number from the set 1, 2, 3, 4. Now, we should end up with 8 possible outcomes. That's because there's 2 from flipping a coin, we could get heads or tails, and 4 from drawing a number from that set. So I'm going to have heads 1, heads 2, heads 3, heads 4, tails 1, tails 2, tails 3, tails 4, and there are 8 possible outcomes. All right, let's try number 2. Draw a tree diagram that represents all possible outcomes from rolling a die and selecting a letter from the word math. All right, well, rolling a die gives us 6 options, and this gives us 4. So we should have 24 total possible outcomes. So let's draw 1, 2, 3, 4, 5, 6. Leave yourself some room. And from each one, I'm going to draw 4 branches. So if I had rolled a 1 on the die and then select a letter, I could get M, A, or T, or H. And now I'm just going to repeat that process for the remaining values. Okay, and again, now you can see our 24 total possible outcomes. All right, number 3, Jessica's getting dressed. In her closet, she has 12 shirts, 4 pairs of pants, and 4 pairs of shoes. How many different outfits can Jessica make? Now, we certainly could create a sample space or tree diagram, but it would be quite large here. What our best bet is to use the fundamental counting principle, which says to multiply the number of options. So she has 12 shirts, 4 pairs of pants, and 4 pairs of shoes. So if we're trying to figure out how many different outfits Jessica can make, we're going to multiply those, and we're going to get 192 different outfits that she could make. All right, number 4, if randomly choosing a letter from the alphabet and randomly choosing a whole number from 1 to 10, how many possible outcomes are there? Well, when we pick a number from the alphabet, we have 26 options. When we choose a whole number from 1 to 10, we have 10 options. So that will give us 260 possible outcomes. Okay, number 5, what is the probability that a vowel, A, E, I, O, U, is selected when randomly drawing a letter from the alphabet? So we want the probability of a vowel, that's the event we're looking for, and it's the number of favorable outcomes divided by the number of possible outcomes. Well, the number of favorable outcomes is how many elements we can select that will actually meet our criteria. So those elements would be A, E, I, O, or U. So there are 5 favorable outcomes, and there are 26 possible outcomes because there are 26 letters in the alphabet. So our probability would be 5 over 26. Number 6. What is the probability that when rolling a die, it lands on an odd number? So the probability of an odd number, well, there are 3 odd numbers on a die, right? 1, 3, and 5. And there are 6 possible outcomes. And we could reduce that 3 over 6 to 1/2. Number 7, a box of 25 donut holes has 10 chocolate, 8 glazed, and 7 powdered donuts. When choosing at random, what is the probability that the donut hole selected is glazed? Well, we have the probability of a glazed donut or donut hole is there are 8 to choose from out of 25 total, so 8 over 25. And last problem, what's the probability of choosing a heart or a queen from a standard deck of playing cards? So for some people, the playing card questions can definitely be a little tricky. So the probability of a heart or a queen. Okay, the first thing I want to mention, I'm actually going to do the denominator first. A standard deck of playing cards has 52 cards, and we're going to put that as our denominator. Now let's determine the heart and queen possibilities. So for heart, that's one of the suits. There are 13 hearts. Okay, and I'm just going to make a note here. That would be 2 of hearts, 3 of hearts, 4 of hearts, and so on. I'm going to list all of those options. And you'll see why I'm doing this in a second. But we also want to know the possibility of a queen. So there are 4 queens, right? There's the queen of hearts, diamond, we have spades, and clubs. So the only thing we want to note here is that we have already counted the Queen of Hearts, so we just don't want to count it twice. So there are 13 hearts and then 3 other queens we could choose from. So it would be 16 over 52. We could reduce that, divide both of these by 2. We would get 8 over 26. Reduce that again, and we would get 4 over 13 as our answer for number 8.